Okay, good morning or good afternoon or good evening, everyone. Welcome to Professor Donald Dingwell's opening seminar presentation for our project group, Quantifying the Global Risk of Volcanic Eruptions to the Airline Industry. My name is Nicholas Saul. I'm the Director responsible for Arts and Humanities, multidisciplinary IAS, and it's my privilege to introduce Professor Dingwell today. Now, as a rule, the IAS only gives minimal introduction to seminar papers, as you'll discover as our term goes on. But since this is the first presentation of the group, and we've had only one paper so far, I will say just a little bit about Professor Dingwell before he proceeds. Professor Dingwell's path has taken him from a PhD in geology and geophysics from Memorial in Newfoundland, Washington, Toronto, Bayreuth, where he did his habilitation or second doctorate, and currently chair at the LMU, the Ludwig-Maximilians-Universität in Munich, where he founded and serves as the director of the Department of Earth and Environmental Sciences. There, amongst other things, he's somehow found the time to become a member of the Leopoldina, or German National Academy of Science in Jena, northeastern Germany, and to serve as Secretary General of the ERC, the European Research Council, an organization close to the heart of most researchers in post-Brexit Britain. In the wake of the major eruption in Iceland in 2010, which disrupted commercial airline flights for many weeks, the Volcanic Ash Risk Project looks at both emergent models for volcanic eruption risk and the responsive system's resilience in the financial structure of the airline industry. Professor Dingwell's talk today is entitled Volcanic Ash in the Earth System, Environment versus Technology. He's going to talk for approximately 20 minutes, whereupon we have the opportunity to discuss the paper for up to an hour in total time or so. Now, you can speak your questions anytime after Professor Dingwell has finished his talk, which you'll get through screening, of course, or you can relay your comments through the Zoom Q&A function, and I will pass them on in my own voice after the paper to Professor Dingwell. And so, Professor Dingwell, over to you.
Thank you very much, and greatly appreciative of the opportunity to be a member of the Institute of Advanced Studies. It's a tremendous tragedy for me not to be there physically, but compared to other things going on the planet, we'll accept that, and very much look forward, nevertheless, after this semester, in the next semester, to being able to visit, and would be delighted to meet as many of you who are resident in Durham during one or more visits that I would like to arrange when things become normal again.
Good morning, good day. It's a pleasure to speak to you today. My name is Don Dingwell. I'm from the University of Munich, the Ludwig-Maximilians-Universität, and I'm honored today to be able to say a few words in the form of a short seminar regarding the topic of collaboration with my colleagues at Durham during the tenure of my IAS fellowship. And it revolves around a very peculiar material, one of the materials that most of us never give a thought to, and that is volcanic ash, finely divided volcanic rock, which is the product of explosive volcanism, and its role in the Earth system. And I've put the subtitle Environment versus Technology under there to try to provoke some discussion at the end of my presentation. So if we look at the problem as a synopsis, essentially an eruption of a volcanic system on the Earth, which is a fundamental and continually reoccurring process in geological history, is a punctual event, which is represented here by a one-dimensional red line. And it is the conversation, if you will, between the lithosphere, which is the rocky sphere underneath your feet, and everything above. And above, of course, there are very many things. And we can start by reminding ourselves that the atmosphere and the hydrosphere are other major reservoirs of chemistry and of physical state of matter in the Earth system. And the biosphere, of course, to which we belong ourselves. And all of these things are impacted by volcanic eruptions in more ways than we have yet even recognized in all likelihood. And of course, because we live in the age of high technology, or at least that's how we perceive ourselves, these technologies basically can be described as a technosphere in which we live. And this technosphere, as it reaches out further and further to higher tolerances, to greater precision, to higher performance for greater efficiency, also in the interest of protecting the environment, nevertheless can become more susceptible to impacts by unforeseen aspects arising from the natural environment. And one of those is the case of the interaction of ash with jet turbines in aviation. So this is a problem that is well known to all Europeans, at least since about a decade ago, when we had the major shutdown of European airspace, which led to very large losses for airlines at the time. And I could say until the advent of the pandemic was viewed as one of the greatest things that could go wrong with civil aviation. There are many things that putting a finely divided dust of rock into a turbine will generate. And I'm sure you can appreciate that this is probably a very ugly picture for most of us to imagine. That's accurate, I think. First of all, you have sandblasting of all surfaces which are exposed externally, including windscreens, which leads to reduced visibility. Secondly, you have erosion of certain surfaces, such as antennae. You also have the potential for plugging up the indicators which are exposed to external atmospheric conditions. We have the potential for erosion of actual parts of the turbines, compressor blades, and rotor portions. We have the potential for blockage of the very finely percolated, if you will, or perforated parts of the turbine, and also the fuel nozzles and the cooling passages is what I refer to with this perforation. You have the contamination of any kind of fluid system, which is a fundamental part of a functioning turbine, whether that be oil or whether that be actual gas mixture. And of course, and ultimately you have the chronic problem of the ash, which is deposited onto the hot surfaces and does not leave quantitatively afterwards. It remains and causes destruction at the site. To take a step back from this graphic example of the impact of geomaterials on technologies, so remind ourselves it's a global problem. Don't think that that is of any surprise to people who have traveled a lot in their lives. We have, for example, in South America, all along the West Coast, a very heavy concentration of volcanic activity. We have countries such as Peru and Chile and Colombia that are basically volcanic countries. In Asia, we have Indonesia, nothing more than a string of volcanoes, one after the other, across a landmass, if you remove the water between the islands, the size of the United States. We have all around the Pacific, including the North Pacific and including the Northeast Pacific, an unbroken string of volcanoes, more or less, all the way from San Francisco to Tokyo. And of course, the Philippines is the continuation of that. So the North Pacific corridor, the North Atlantic corridor, which goes over Iceland, these are all areas where planes every day are flying over volcanoes. We try to break down these processes in the laboratory. I'm an experimental scientist. I'm a deterministic dinosaur, if you will. And we try to establish cause and effect in the physical response of these materials. And you might think that the eruption of a volcano is a very simple matter, but actually when you break it down into its constituent parts, it is fairly complex. And this complexity is something that we can expect will give rise to the observed high variability of the products of explosive volcanism on the Earth. So here is just a one-dimensional linear expression, if you will, of the quasi-sequential set of circumstances which occur in an explosive eruption. We have a saturation of the volatile phase, largely composed of CO2 and water. It leads to nucleation of bubbles. These bubbles grow as the ascent occurs through decompression and through diffusive feeding of volatiles which are oversaturated in the melt. It leads to eventually to a foam which generates materials such as ash and pumice, and of course the fragmentation where these materials snap from being a highly vesicular and viscous flow into being a dusty gas, which it makes its way up the pipe and out onto the surface of the Earth. Inherent in the whole story is the fact that there's a duality in the behavior of molten rock. These materials are relatively high in viscosity compared to most liquids that you encounter in your daily lives. And as a result, we have two regimes to their behavior which are easily accessed in nature. We have the liquid regime, which is in the upper left, in the brownish color, and we have the glassy regime, the solid response regime, in the lower right. And this yellow stripe running through the middle of the diagram is what we call the glass transition. It is where all industrial glasses are produced, and it is also where the glassification of magma takes place during an explosive eruption, such that we actually produce glass shards as the result of the process. And here you can see two examples of what volcanic ash can be composed of. If you look at the upper left, you see very porous, drawn out bubbles which have been broken and exposed at the surface. This is what we would call a tube pumice. And at the lower right, you can see in transmitted light, crystals, individual single crystals, which are characterized by a very irregular internal structure that you can recognize, but also broken glass shards, for example, here, which look very similar to the appearance that you would obtain if you took a piece of the window glass, the room that you're sitting in, and ground it up in an agate mortar. Ash is by definition less than 2 millimeters in diameter. It's a very trivial definition of volcanic ash and volcanic processes. And here you have viscosity versus weight percent of water increasing to the right. And it points out what a playing field we truly have when it comes to magmas ascending in a volcano, because they ascend from conditions near these chemistries up to conditions near these chemistries. And by moving from the right to the left, you can see that you're confronted with this rising wall of viscosity. So these things stiffen enormously on the way up in the conduit. And this is what generates eventually the transect through the glass transition and the fragmentation of these materials. And just to give you one example of material which is in the beginning oozing like a glacier on top of this volcano in Japan, moving so slowly that you cannot see it. You would have to measure it with a creep sensor detector. But what you see is that it reaches a crisis, and as a result, it collapses. And when it collapses, it not only breaks into particles, it also, due to the overpressure in the bubbles in this porous material, has much more explosive power, and you get a much finer grain size distribution as this material runs down the valley. And of course, these are the deadly pyroclastic flows which can kill you by burning, by burial alive, by ingestion of ash, and several other ways. So I'll cut it short. So we try to characterize the material properties in these systems very, very precisely using materials techniques, material science techniques. And what you see here are two examples, one of a low viscosity device and one of a high viscosity measurement technique known as the dilatometer. And by using these different techniques, we can actually characterize the viscosity temperature relationship. You see here the logarithm of the viscosity versus the reciprocal temperature. So hot is on the left, cold is on the right. And you see that there is a wide range in log units, a very wide range of viscosity at any given temperature within the range of natural compositions of liquids, which are represented here by total alkalis versus silica. So I'd like to take you experimentally on a fast transect of the glass transition. You've seen a mountain collapsing in nature. Let's see what we can do in the lab. This is a fragmentation bomb, which we use to capture the particles which are produced through what we call successful fragmentation and ash generation. This is the lower plate of this bomb covered with newly produced fresh volcanic ash. We do it from magmatic conditions of pressure and temperature, up to 1,000 bars, up to 1,000 degrees Celsius. So we're literally there in terms of the pressure and temperature decompression rate that we need to be in order to reproduce the fragmentation of a volcanic dome. And if we look into the device by doing analog experiments using rock at room temperature, you can see the kind of process of fragmentation that we're actually generating, running on now for a couple of milliseconds of total video runtime that you're seeing here, slowed down using data from a high-speed camera. So this is literally the process which you saw on that volcanic mountain in Japan in the previous video. And of course, if we look what happens in the tank above, which is there to catch whatever comes out, here comes the gas, which has set the pressure on the sample, and then it's followed by a pyroclastic blast. And we see these things in nature all the time. This is the routine expression of explosive volcanism in nature. Fragmentation of rock is the defining feature of explosive volcanism. So this ash goes into the Earth system and produces a tremendous, a prodigious potential complexity in terms of the things that it can contribute chemically and physically to the ash-Earth interaction and the consequences that it can bring with it. And I can pick any one of the examples here, but really all I want to do with this diagram is impress you with the potential complexity of ash contributions to the Earth system. And this is all the natural Earth system with minor contributions of technology such as roofs of houses and other such things. There's no high tech on this diagram yet. So we have ways of generating ash, as I've just shown you. We also have ways of seeing how the ash is affected before it gets out of the vent by interaction with the gases, the hot gases which are coming out with the ash, which are also highly reactive. So we have a tumbler here, which we built for ash gas reaction, solid gas reaction, standard technology. We can see that the surfaces of the ash particles are covered with precipitates of sulfates, just as we see them in nature, so that this ash which comes out is not simply, to use the word somewhat ironically, it's not simply a mixture of glass shards, gases, and crystalline phases. It's also precipitates which are formed by the reaction of those phases with each other as it's come out of the vent. And of course, the ash is dispersed. And it's the game of meteorology to figure out how the ash will be dispersed, because it strongly depends upon the prevailing wind, and the wind conditions, and the height to which the ash will rise, and which section of the column of wind direction will be accessed by the ash cloud. And so you have here, for example, a very, very focused ash cloud, which has maintained its compact density far, far away from its eruption from the initial source of the volcano. And we can paleo reconstruct these ash clouds by looking at the density of the deposits that they leave, because the ash falls from the sky eventually, and we can therefore say how much was transported, how far, with what grain size distribution. But we even have complexity in what seems like a very simple classical physical task of doing reconstruction. Here you see three events where we have it, a volcanologist under an ash cloud looking at something happening as these ash particles fall. And I'll show it to you again now. You probably missed it the first time. Look at the circles, 1 and 2. And I hope you were able to see that we had very large aggregates of ash which were bound to each other somehow, either chemically or electrostatically, and which disintegrate when they hit something as soft as somebody's finger on the way down out of the ash cloud. It means that when we go to do the paleo reconstruction of the distribution of the ash, we can't determine all physical parameters from the dispersal of the ash column, while because this dispersal is something which is also impacted by these clusters, which are no longer in the geological record once they've hit the hand. So the problem of this ash going into the technosphere, and in particular into aviation technology and into turbines, is a twofold one. There's a physical problem and there's a chemical problem. The physical problem is first defined, the entry fee, if you will, to understand it, is to understand what will happen if I take volcanic ash and reheat it in a jet turbine. Excuse me. And if I do, as a function of temperature and chemistry of the ash, you will see that the ash is remelted to form liquid beads, which then wet the surface of the ceramic, which is the protective surface, the so-called thermal barrier coating, which resides on all turbine blades in order to give them high temperature refractory behavior. So what we see is that there is a great variety of the temperature dependence of the ability of these systems to wet. On the right-hand side here, we have volcanic ashes, and on the left-hand side, we have quartz sand, which has a much higher resistance in temperature to remelting due to its high melting point. So the basic message is here, we have a situation where the melting temperature of the volcanic temperature at which these ashes have been ejected is lower than the technology that they encounter in the jet turbine. And you know that can't be good. The second problem that we run into after the physical interaction, which can lead to spallation, which can lead to fragmentation of the thermal boundary or barrier coating, is illustrated here. Here you have a very simplistic cartoon of directed crystal growth, which is one of the elements of the composite layer structure of these ceramic layers, which are deposited on superalloys in turbine blades. And what we have is a molten ash, which has now adhered to this surface, and it will begin to chemically react. And so this is the second great challenge. It's to understand how will this chemical reaction proceed? What will be the phase equilibria controlling this? What will be the kinetics controlling it as well? And can we design new and better types of thermal barrier coatings so that they can be more resistant to degradation, if you will, by molten volcanic ash? We can split the whole problem at the end of the discussion into two different parts. And the two different parts are the acute and the chronic hazards to turbine technology. Thank you very much.
Well, Professor Dingwell, thank you so much. You said it was brief, but it was also rich, and I was gripped by that. Well, let's move to the discussion now. I think you'll all know the routine. I'll just recap very briefly. If you would like to ask a question, just raise your hand virtually and then unmute yourself so we can have a bit of a sequence. Do I have any questions or comments? 5 questions, that is. Okay, let me kick off. I've already revealed in our conversation before this session that I myself have published an essay on volcanism in literature. So I have a dangerous amount of very small knowledge of this. And my question is, I found it very interesting, Professor Dingwell, the way you reconstructed what happens to ash on its way through the meteorological system into the technical system of the jet engine. What about one step further back? Is it possible to predict when a volcano will blast? Or is that such a complex system of relations between elements that it's non-linear, it's a non-linear tipping point, and we're not quite there in predicting when a volcanic eruption will cause that sort of trouble.
So as you can imagine, Nick, this is a question that we always get, and we are in principle well prepared to answer. I do it in a way which I think is very different than everybody else. I would compare the research into the prediction or the forecasting of eruptive events with medical research, something that everybody has I think a closer intuition on. And that is that there are multiple sources of influence on whether or not a particular event will occur in a volcanic eruption. A volcano has its own nature. The magma which the volcano is composed of has its own properties, including the stress distribution within the magma. A volcano is also in a certain place, which has its own local regional stress field, and its local geothermal gradient, and its local physical state of the rocks into which the magma has arrived, has its own geology. Every spot on the earth has a different geology. And if it's a chamber in which the volcanic material is residing, then you can imagine that there must be some degree of individuality of volcanic behavior. Volcano also has a certain age. They evolve from relatively low viscosity liquids to higher viscosity liquids in many cases over time, which means their explosivity can increase with time. So there are many aspects. There are 4 or 5 at least fundamental physicochemical aspects, internal and external, which influence exactly what will happen in a given place on a given day. And it's quite important to realize that external factors that I've just mentioned are ones which will never be arrived at in terms of predictability if we only focus on the nature of the volcanic material itself. And we have many famous examples of what we believe were external triggers of significant eruptions. So again, coming back to the medical analogy, I hope you can appreciate now that it's a little bit like going to the doctor and getting a diagnosis. I heard a joke the other day that a gentleman wanted to get a second opinion, so he went back to the doctor, the same doctor. But if you let that sink in, there's actually a bit of that as well in what we understand about volcanoes. But if you go to the doctor and you ask him how long you're going to live, he cannot tell you because it depends upon several things. It depends upon your behavior, depends upon your genetics, depends upon the external circumstances in which you lead your life. And you can get a diagnosis from the doctor. You can leave the doctor's office. You can walk across the street and be hit by a truck. And as I say to my students, this happens to volcanoes as well. So if we have a major landslide on top of a volcano, just to paint a picture, to illustrate what I'm trying to say, this is something that will not be predicted from the state of the magma, at least not easily. But are we getting anywhere in medical research? Sure we are. We're making progress in genetics. We're making progress in epidemiology, probably the field of medical research that everybody loves to hate. It's statisticians versus all other physical scientists, so to speak. But the same thing, exactly the same sort of circumstances exist in volcanic research. We look for empirical sources of information on what the volcano has done in the past. We look for the epidemiology of volcanoes. What can we say statistically about the likelihood of events and event size versus frequency and repose time between events? We monitor, of course, and that's the big business financially of volcanology. We monitor volcanoes physically, chemically, and in terms of the form of the structures using what we call geodesy. A lot of it satellite-based today. And then we try to take this salad of mixed physical, chemical, and geodetic signals and pull out something which indicates that the volcano has gone into a phase of what we call unrest. And volcanic unrest and management of volcanic unrest is really if I can say it, it's the most promising way of trying to grasp whether or not we will be able to predict major events in the future. Because if we understand that this volcano has, quote, a disease or a pathology, then we have a chance perhaps of coping with it, or at least predicting its outcome. And so the more I use this analogy between medical research and are we seeing progress? Yes, we're seeing decadal progress. Have we got a cure for cancer? Probably the wrong question. Are we improving the lives of those who live with indications or indicators of cancer? Yes, we are. In the same way, we're trying to improve the lives and improve the predictability of the lives of people who will be most directly affected by volcanic eruptions. That does not mean that I've uttered the last word on volcanic prediction, and I certainly don't have the last word, but that is the status in which we operate now.
Thank you so much. I have had one signal of a question from Veronica Strang. Veronica, would you like to unmute and ask a question?
Yes, thank you, Nick, and thank you for a wonderful explanation there, Don. I now have a wonderful picture of just how scary it is in terms of what volcanic ash does to airplane turbines. But it does sound like one that's extremely difficult to solve. So it sounds like planes simply shouldn't fly through volcanic ash at all, and which leads me to a couple of questions. One is more philosophical and one is more practical. I imagine that it may be more feasible to predict how long it will take for ash to precipitate and land safely on the ground, where I know it becomes wonderful things like fertile soil, having lived in New Zealand for many years. But it's also, I'm interested in how you're presenting the problem as in sort of disease terms, when it's clearly a sort of process that happens naturally. And it would seem that what we're trying to do is think about how to deal with what is actually a very natural process of eruption and pollution by trying to predict it. But in fact, it sounds like a problem we kind of just need to work around on a kind of ongoing basis. So it's partly a philosophical question in that way.
Yeah, no problem. I think I've understood what you're saying. Of course, disease is natural too. Viruses may have been the key to the origin of life. I mean, there's a lot of stuff out there, RNA world and so on and so forth. And now we're playing with mRNA in order to save ourselves from what we think is a pandemic. What we're sure is a pandemic, excuse me, but it's all a very anthropocentric view of everything, of course, that guides at least a half of our university in any major university, right? I mean, that's the conundrum of big places like the University of Munich. Half of us are looking outside from the human condition into the natural in some way, physical, chemical, whatever, and the other half are studying our condition. So stepping into your question about whether it's a natural part of the system, absolutely. If there is a way to underline what I would say about volcanism, it is that we live on a volcanic planet. And in fact, everything we know from all of the terrestrial planets that we can see, in quotation marks, including Venus, is that they're all volcanic. They're fundamentally volcanically built. The origin of their oceans and atmospheres are probably volcanic. And so one can go deeply philosophically into what it is that the thermal conditions of our planet, combined with the rocks that make up its interior, yield to its melting routinely, and therefore processing valuable volatiles to the surface of the planet. In the same way, living with volcanoes is something we've been doing since the origin of species, and certainly since the origin of man. And the luck that we've had in plucking out most of the earliest fossils related to our origin is all to do with them being caught in volcanic eruptions, which have deposited the things in volcanic ash. It's a fantastic story. And I've seen research projects on East Africa where one has tried to define or understand that portion of the ascent of man in terms of its intimate proximity to volcanoes. So yes, we are living on a volcanic planet. We will not stop volcanic eruptions in the future on a grand scale. They come from, at least not within a conceivable period of time, perhaps in centuries into the future. We'll be under different circumstances, but by then I suspect, and I hope, we'll have a different view of how to manage the Earth. And then the question will be whether one wants to influence the trajectory of natural processes on the Earth so deeply so as to avoid a major eruption. It's a very interesting philosophical path to walk down to decide if we could do something about, if we could do volcano engineering. And I'm sure you can immediately grasp what would one want to engineer about a volcano? Well, the first thing that jumps into your mind is when and how it erupts. Would we do it? And this is actually a question which we're beginning to speculate about now, perhaps the same way that, Goethe would have speculated about whether these things were high temperature liquids before he could actually see the processes stumbling around in the forests of Central Europe. We are speculating now that we might try a minor intervention at a few kilometers depth in Iceland, where we know it exists because we've accidentally hit it with drill holes in the past. Drill holes which are intended for geothermal power have struck live magma. And you may say, well, what defines a live magma? Well, it starts coming up the hole. There's nothing difficult about any of the pictures that I draw here. So this is the threshold that we're sitting on right now. I'm a proponent of trying it. I can imagine, or I can guess how, that doesn't appear appealing to those who would say interfering with the natural state and appearance of processes on Earth is surely not the path that we can go down. However, there are also strong economic reasons for simply seeing whether or not we can reliably be in the vicinity of a magma body without being endangered by that fact, because there's a huge amount of energy to be pulled out of it. So I can start climbing my way, if you will, out of the intellectual well or the philosophical well by saying, well, this is a huge source of power, which we can have. It in no way will negatively influence the environment that we can imagine. It will slowly enhance the cooling of the crust where it happens, but we're doing it. Under Munich in 10 years, I've been told there'll be 7 major companies that are pulling heat out of the northern alpine folds, which are here. Large sections of Munich today are heated by low temperature geothermal energy, but high temperature geothermal energy is at least 10 times as efficient in a purely engineering sense. So we're actually on the cusp. Your question has brought me to say that we're on the cusp of thinking about whether or not we want to try to intervene and see, first of all, whether we can do it. That sounds now very, very, I don't know if that sounds like it's out of time, such thinking, but at the same time also to see what will be the consequences of trying to do it. And I'm pushing very hard for this on a European scale. We will see whether or not we'll be, and many people in Britain are actually quite involved in this as well. And we're trying to see whether or not this is something we can do. Your second question, or did you have a second question, Veronica?
No, it was a very simple one about whether you can predict how long it will take for the material to precipitate so that things can get back to normal.
So maybe just coming back to Earth for a moment, because I went on a rant there, but which is common to my culture back home. When we talk about predictability, we can talk about predicting very small events, which are very repetitive, which happen. For example, Etna is guaranteed to erupt within 5 years, wherever you are, whenever you are. Those sort of things we can predict relatively well because we have hundreds of examples which we've monitored well, and we know what it looks like when one's coming. If I'm worried about whether Yellowstone will erupt in the catastrophic way that the media often paints it, that the Western United States is covered in a blanket of 2 meters of ash, very difficult because we know that it only happens once in 500,000 years to 1 million years. So we've never seen it happen. Mm-hmm. In fact, in the history of man, there's nothing really historical comparable to it. There are prehistoric eruptions which approach it in size, but we're going back 70,000 years, and we're going back to DNA bottleneck and why we're all too related to each other. But it may be that near extinctions of man in the past have been related to some of these global events. It may be that the fall of the Neanderthals in the end was impacted by a major eruption in Italy. There's fantastic examples that we have, which may relate our own history and prehistory to individual identifiable volcanic events. Justinian's plague and many examples.
Okay, I have two questions in the pipeline, both in fact from IAS colleagues. The first one is from my colleague, Professor Laszlo Poulos from Business Studies faculty, and the second is from Ronan O'Donnell. So Laszlo.
So I was puzzled about the energy source of the magma, not as an energy source for ourselves, but what heats the magma. And quite clearly, it should be some nuclear processes going on in the center of the Earth, such that the nuclear fission basically heats up the rock and generates this sort of hot liquid. And now the question is whether there is any threat associated with the nuclear radiation connected to the outflow, either in terms of the magma or in terms of the ash.
Yeah. The first of all, the ash is the magma. It's just in another form, physical form. So that's the same question. The Earth is there's a substantial source of heat in the Earth, which is radioactive decay, fission, as you say. We have long-lived isotopes that have half-lives which approach the age of the Earth. And that's the way that we know how old the Earth is, because we use them to measure to-date meteorites, which presumably were formed and then frozen, and therefore represent the first gasp of chemistry, if you will, in the solar system. So we have this. We have many long-lived isotope systems in the Earth. We have uranium lead, we have neodymium samarium, we have hafnium lutetium, we have tungsten rhenium. These are all parent-daughter pairs which have long, up to hundreds of millions of years half-lives. That's a fundamental physical aspect of nature which gives us a lot of heat in the Earth. There are also major sources of heat from potassium, from thorium, and so on. The amounts of radioactivity which occur in deep rocks are nothing compared to what we were able to artificially produce, of course. Today, the only danger which comes from natural radioactivity that I can think of, which is widespread, which is that if you have crystallized volcanic systems which have frozen at depth, then they form granite as a typical product. And there are, as you probably know, many terrains across the Earth where people build their houses on granite. And if you have granite and a thin soil layer, then you can capture significant radon from decay of radioactive elements. And then you have this classic problem where people are trying to build radon maps of Europe now, for example, in order to make sure that they have proper ventilation of basements in houses. So you do have this low-lying enhanced epidemiology of cancer in areas where you have high radon in the rocks which form the basement upon which houses are built. You also have natural radioactivity when you drill for oil. People don't talk about it very much, but when you pull a lot of material through a pipe bringing oil field production to the surface of the Earth, you actually have a lot of precipitation of junk which doesn't want to be at one bar. It was at higher pressure at depth, and it's called scaling. And this scaling has to be removed from the pipes routinely, and it tends to be quite substantially enhanced in radioactivity. But these things are local, and in the case of the oil production, of course, this is a much lower temperature phenomenon, nothing directly to do with volcanism. Why do we have the volcanism? Because it's hot at depth, as you rightly infer. And it's simply a competition between the geothermal gradient and the melting curve of whatever materials are at depth. And we have at depth several degrees of heterogeneity, Laszlo, so that in some places the material is melted and in other places it is not. So the Earth is largely solid, but we have a substantial amount of molten packages within the Earth. And of course, there's a huge geotectonic cycle explaining all of this and why it's still going on Earth, whereas it appears to be dead on Mars and so on and so forth. But the fundamental heat that we're talking about when we talk about geothermal energy from magmas is simply the advective transport of hot material from depth due to buoyancy to higher levels in the crust.
Okay, thank you very much. We have still 2 questions in the pipeline. I think Fabian may have been waiting for a little while now. Fabian, do you want to go first?
Sure. Thanks, Don. I was wondering, because in both your talk and your answers to some of the questions, you've sort of brought to the front of our minds just how complicated volcanic systems are, and I would agree with that. But then in your talk, you also sounded positive about the future in terms of the relationship between an airline industry and a volcanic planet. I wonder if I'm maybe a bit more skeptical, and I just wonder the degree to which you think that interaction between aircraft and volcanic ash is a tractable problem, and especially kind of thinking about if you were a policymaker who had to decide to fly or not to fly. Do you think that this kind of fundamental research that you gave us a kind of taste of at the end of your talk, do you think that has the potential to change policy and change the rules about what airlines can do and ultimately save the airline industry money as a result?
It's a very difficult question for me to answer your last, what your last sentence posed, which is, can we, through our efforts, have the opportunity to influence the behavior of those who are responsible for financially, if you will, for the risk? That is really the far end from, as I said earlier, this deterministic dinosaur that you're speaking to. And so that is where I'm least qualified to say what our chances of success are. But I do want to say that I want to refer to 2 aspects of which you brought to mind for me. First of all, when we're talking about developing new and better barrier coatings, for example, these bring us to higher temperatures of operation of the turbines. The higher temperatures of operation of the turbines bring us greater efficiency. And efficiency is something we're all chasing, especially in terms of energy use, to bring ourselves to a world where we have less impact on the environment, despite using it in a high-tech way. So this is one of the reasons that we're pushing to higher and higher temperatures of turbine operation. But with it, of course, brings the higher and higher and higher challenge of dealing with the potential interaction with environmental dust. I should say it's not just volcanic ash which forms the problem. We have, in any environment where we have dust during takeoff and landing, especially, where we have problems of accumulation of so-called CMAS, calcium magnesium aluminosilicate, melt and glass formation on rotor components. So we're running into this in deserts. We're running into this also in any area where there's a significant amount of ground aggregate material, ground near aggregate material in these systems. So it's a much broader topic. And in fact, most of the people who work on the influence of these molten materials on turbine components say that volcanism is just a small part of a much greater problem. The second thing that I wanted to say was that, yes, it is a little bit Formula One, what we're talking about here. And if you have your Volkswagen Beetle, which still runs after 40 years and you can drive it well, why do we bother? And of course, I don't need to answer the question. You know that we do apparently bother in most areas of highly developed technology to make them better and better and better. This has elements of efficiency, but of course it also has elements of performance. And you probably have heard as well as I have about what the ambitions are for aviation, which are to go back to 4 hours across the Atlantic in the near future, or 3 hours across the Atlantic. And we haven't said anything today, and I don't really want to say anything today about the non-civilian aspects of aviation. If I can put it in a silly way from a social scientific point of view, those who have to fly those who don't have the choice of not flying, perhaps in certain circumstances. So there's although I'm not related to it directly myself, I'm sure that there's a large push and a large amount of activity from the side of governments trying to make sure that they have the best technology for high temperature turbine operation in situations where it's not only civilian in nature.
Okay, Fabian, did you want to come back on that?
No, that's great. Thanks very much. Thank you.
Okay. Ronan, do you still have a question?
Yes, I do. Thank you. I found that really interesting. Thinking from, I have an archaeological background, so the interaction between humans and technology and environment is the sort of perspective that I come at things from. I thought the diagram that you showed right at the start with the lithosphere and the biosphere and so forth, I think that was an interesting sort of conceptualization. So thinking in those terms and thinking in an historical, way, I was curious about where this seems to be a threat that exists only because humans have particular types of technology and use them in particular ways. So I was interested in where this threat fits within the history of aviation over the last 117 years. And so how this affects piston-engined aircraft and aircraft flying at low altitudes, because high altitude flying and jet engines are relatively recent technologies. And so is this something that a threat that we've only experienced as humans since the last sort of 50, 60 years, or is it something that's present to some extent or to a lesser extent through the whole history of aviation? So really is is this threat different for aircraft flying at lower altitude and with piston engines?
Very good question. I'm not at all an expert on it. We may have somebody in the round who knows much more than I do about it. I really can't answer your specific question at all, except to say that we would have a chance to archaeologically discover the answer. Okay, it would give you hope there that we could probably reconstruct were it to have been the problem that you're speculating upon. In terms of older technologies of not flying but other things, of course, we've always, whether it is your mud hut or your straw roof or your sheet metal roof today in Indonesia, our technologies have always been sensitive, of course, strongly sensitive to the environment. And people who work in volcanic risk produce maps of expected loading of different roof types based upon volcanic ash. And they actually will, from styles of construction in particular areas around volcanic centers, they will produce maps of risk based on that. Plays into the insurance, to the calculation of insurance costs associated with it. So that's just a rather trivial example of the technology, but that is even not to say, of course, that some of the first technologies that we have are related to, of course, rocks. It's what we name our earliest prehistoric periods after in the ascent of man, and of course, volcanic types of rocks are the center of all of it, going back to the obsidian trade and so on. Not to mention the first glass making, the first smelting.
Thank you.
Okay, we have 2 or 3 minutes left. Now is your chance to ask another question.
I'm just thinking about how you could use past eruptions in the geologic record to predict these sorts of things. And I know you mentioned, Professor Dingwell, about how ash aggregates could actually disintegrate on impact with the surface. I'm just wondering, to what extent is this actually a problem for surveying ash particles when you go out into the field, and how could you actually account for this? And are there any assumptions you take to assume this?
Yeah, so I'm not a modeler of ash dispersal. I should say that at the outset. And there are some very smart people around Europe and around the planet who are. So everything that I say to you now is please to be enjoyed with caution. But the fundamental problem is that if I go to the field and if I measure a local ash sample, then I not only am interested in how much I have, which is of course very important, and producing what we call the isopac maps of thickness of these deposits. That tells me the volume, the dense rock equivalent, as we call it, which can be up to thousands of cubic kilometers, by the way, but also the grain size distribution, because that will tell me, one would hope, if one had the original grain size distribution, that one could infer the meteorological conditions which led to the deposition where it took place, and perhaps also the height of the plume and so on and so forth. The number of things that one would try to derive. In principle, people who are doing paleoeruptive studies using ash deposits try to derive everything that they can from the deposits, naturally enough. And that involves such topics as the height of the column, whether or not there was ice nucleation on the ash particles, all kinds of things. And a lot of this can be lost if one of the most fundamental and perhaps the most widely determined aspect of ash deposits, their grain size distribution, is distorted with respect to the physical the state that it had of physical properties when it was deposited. So if there's a mismatch between the physical state during the process that you're trying to model and the physical state that you have to model it, then you have to try to reconstruct it in order to fully understand that part. And that's the rub, because some of these things disintegrate, we suspect, with no obvious record of having been aggregated. That was the point I was trying to make.
Okay, I'm afraid we've now reached our tipping point ourselves, and we've definitively run out of time. Quite a number of people have run out of our chat room to go and teach classes in the Greenwich time zone. So it falls to me now just to say thank you very, very much for Professor Dingwell for his talk. It's been very stimulating, and we look forward to other contributions from this group, from other members, and participation also from other groups. One last thing I'd like to say, the next IAS virtual event is by Fabio Mazzacchi, who is going to be lecturing on Tuesday, 20th of January, 1700 GMT, that's 1800 Mitteleuropäische Zeit, on who should pay for interdependent risk, policy implications for security, interdependence among airports. We look forward to seeing you all then, and have a good day, or a good night, or a good afternoon, everyone else.